In this problem, we've got a birthday balloon. We're going to stick it into a freezer. The balloon is about 2.1 liters in volume. Pressure outside the freezer. Inside the freezer are the same, so P1 equals P2 equals 1 atmosphere. The room temperature is 31.2 degrees C, and the freezer temperature is minus 7.8 degrees C. What is the volume of the balloon since it reaches once it reaches the temperature in the freezer? Now, I will warn you, if you do this experiment with your niece's Mylar birthday balloon, there may be tears because it will deflate some, and then it will inflate again once you take it out and it warms back up. But let's take a look at this problem. Well, where do we start? This involves pressure and volume and temperature, and which should tell you this is an ideal gas law problem. And in this problem, one of the things we have to make sure we do is that we convert our temperature to Kelvin, because temperature has to be Kelvin to use this equation, right? Temperature has to be Kelvin to use that equation. So first, we're using P1, V1 over T1, right? The pressure, volume, and temperature we start with for an ideal gas are going to stay the same as in this relationship, right? The pressure can change, the volume can change, temperature can change, but this relationship holds for an ideal gas. And air as a quasi-ideal gas, certainly helium in a balloon is an ideal gas. And we've got to take T1, which is 34.2 degrees C, and we've got to add 273.15 to it to convert it to Kelvin. And we've got to take T2 and we've got to do the same thing, minus 7.8 degrees C plus 273.15 Kelvin. All right, so both of those, we've got to take into account the fact that to use this equation, our temperature has to be in Kelvin. And what else do we have? We have P1 equals P2, which means P1, since P1 equals P2, right? Oh, that's a silly way to write that. Equals P2, I can simplify the equation as just V1 over T1 equals V2 over T2, right? So now I've simplified it. V1 over T1 is V2 over T2, and what it's asking me for is V2. So let's just go ahead and multiply both sides of this equation right here by T2, and that's going to give us V2 is T2, right? Because it cancels out, times V1 over T1. And the physicist in me wants to write this as V1 times T2 over T1, because it's just prettier that way. Okay, so we know everything on this side of the equation, and we're trying to figure out that side of the equation. So we can stick this all in, all right? Let me go ahead and get these numbers, simplify life a little bit. So we have 34.2, and we have minus 7.8, and just to both of those, we need to add 273.15. Okay, so 307.35, 265.35. 307.35 Kelvin and 265.35. 265.35 Kelvin. Okay, and now we're ready to use this equation down here. We're ready to put everything in there. So V2 is going to be our V1, which is 1 liter. Nope, sorry, V1 is 2.1 liters, right? Onto T2 is 265.35, and T1 is 307.35, right? And so we got to pop over to Excel. Our volume is 2.1, so it's going to be our volume times our high temp our second temp divided by our first temp, right? So 1.81 liters. So the strength shrinks about 10%, 1.81 liters. It's not a lot, but it's enough to make the balloon no longer a nice, tight balloon. All right, that's it for our ideal gas problem.